So, today we will discuss the remaining question answers of the exercise section, but one or two examples or exercises that we have already discussed, I will repeat that one once again, as some of your friends have asked me to repeat that one. Means that questions are a little bit tricky questions are that one. So, for the first time it will be take much time to understand the concept and as well the solution. So, one of such a question is that 2.19. So, I will just repeat that one. So, then in a simple way I will repeat explain that one, you can understand that one easily. Okay. So, the question is that as a statement the question is given. Okay. The principle of parallax in section 2.31 is used in the determination of distance of very distant stars. So, we know that the parallax method that we are using to measure the distance between the stars, sun, earth and such kind of things. That means for measuring larger distances. The baseline AB is the line joining the Earth's two locations 6 months apart in its orbit around the sun. So, you know that the Earth is revolving around the sun in an orbital path. Okay. So, that means it needs 12 months to complete one entire revolution. So, if we are considering only 6 months, that means it will start from one point and exact opposite point, on the exact opposite point it will reach. That means half of the path. Okay. So, from here the Earth is starting the movement, okay, the revolution, and it is reaching over here at B by 6 months, and again after 6 months it is reaching the same point at A. So, now in this question we are considering only the 6 months revolution, that is the half of the orbit. The Earth moved, or Earth covered the half of the orbit. So, the distance between A and the B, the initial point from which the Earth begins its journey, and after 6 months it reached B. Okay. So, the distance between A and B will be actually the diameter of the orbit, isn't it? That will be the diameter of the orbit. That is, AB distance is actually B is equal to, it is known as the baseline. Okay. That will be is equal to 3 into 10 to the power 11 meter. So, the radius will be is equal to B by 2. Okay, we need the radius value, remember that one. Okay. Now, however, even the nearest stars are so distant that with such a long baseline they show parallax only of the order 1 second of arc distance of an of arc or so. A parsec is the convenient unit, again statement. So, here to confuse you that 1 second value, that even stars near the so distance, all those things are given. Actually, those data are not necessary for our calculation. The proper question, for the proper question, these data are not necessary. Now, again a statement is given. A parsec is a convenient unit of length on the astronomical scale. The parsec is the unit of length actually, and which is using in the astronomical scale. That means for such a great larger distance we are using the unit parsec. Okay. Now, it is the distance of an object that will show a parallax of 1 second of arc from opposite ends of the baseline equal to the distance from the Earth to Sun. Okay. So, that is the definition of the parsec. In other words, in easier way, we can define the parsec as, parsec is the distance at which the radius of the orbital of Earth subtends an angle of 1 second. Okay. So, parsec is the distance at which the radius of the orbital, okay, subtending an angle of 1 degree, that is the parsec. The distance is 1 parsec. Getting or not? So, here in this case we have to find, the actual question is that how much is the parsec in terms of meters. Okay. So, you have to find out the value of 1 parsec in meter. So, the definition of parsec is that this is the distance which obtained, or the distance at which the radius of the orbital of earth. Radius of orbital of earth is actually here, it is CB. Okay. CB is the radius of orbital, that is C means the center point. Okay. So, that means the distance will be B by 2, that means AB is B, and at the center point is CB. If you are taking that distance, that will be B by 2. The value of B is already given in the question, that is 3 into 10 to the power 11 meter, and the arc angle is how much it is, 1 second. In such a case, if the small d, suppose if you are comparing that with the parallax method equation, so you know that this is the position of the observer, isn't it, and the distance between the points of the observer, if it is small d, and the angle subtended by the viewpoints, if it is theta, then the large distance, that is distance between the observer and the celestial object, will be capital D, and the equation which is relating all three things will, theta is equal to small d divided by d. Okay. Here this small d is actually the radius of the orbital of earth. As per the data, the small d value is actually B by 2. So, you can write the small d is equal to B divided by 2. Okay. Small d is equal to B divided by 2, that is the radius of the orbital of earth, and the theta means we have to take the theta as 1 second, then only the capital D value will become 1 parsec. Okay. Then only the capital D value will become the 1 parsec. If the small d value will be the radius of orbital of earth and theta as 1 second, okay, theta as 1 second, then the capital D will be is equal to 1 parsec, 1 pc. Okay. Now, you have to find out the D in terms of, now you are having the D as 1 parsec, now you have to find out the D in terms of meter. For that, you have to substitute the values for 1 degree and the B by 2 values you have to substitute, then you will get the value of D. Okay. So, already we have proved that one, the D is actually 1 parsec. In parsec unit you know that. Okay. Now, D in terms of meter you have to find. Okay. So, 1 parsec, the question is, actual question is that we have to find 1 parsec in terms of meter. For that, the data that we are obtained now, we can substitute those values and we can find out the D value. Okay. So, for that, first of all you have to convert the second, 1 second, the theta value into the radian. So, 1 second is actually 4.85 into 10 to the power minus 6 radian. Okay. So, now we are substituting the theta, D and D and small d values we are substituting. So, that will be is equal to the theta as 4.85 into 10 to the power minus 6 radian is equal to, here D, small d is actually the distance between the center and the earth, that means the radius of the orbital of the earth. So, that is B by 2. So, D you are substituting as B by 2 divided by the capital D. Okay. So, that is 3 into 10 to the power 11 meter divided by 2 into D. So, that is equal to 4.85 into 10 to the power minus 6 theta. Okay. So, now you have to find out the value of D. So, for D will be 3 into, you are substituting, just crossing the, it means you are just interchanging the left hand side and right hand side, numerator and denominator values you are just changing, and so D will be cross multiplied with the 4.85 into 10 to the power minus 6, and 4.85 into 10 to the power minus 6 will be taken to the denominator of the right hand side. So, D will be is equal to 3 into 10 to the power 11 meter divided by 2 into 4.85 into 10 to the power minus 6. So D in terms of meter you will obtain as 3.08 into 10 to the power 16 meter. So that is equal to 1 parsec. That means where the small d value is the radius of the orbital of the earth and the theta value is actually 1 second. In such a case, the distance between the earth and the celestial object will be is equal to 1 parsec. So now we have found that value in terms of meter. Okay. So 1 parsec we can write 1 parsec is equal to 3.08 into 10 to the power 16 meter. This is the final answer that you have to find. I think now it is clear, it became clear for you. Okay. So actually the concept is very easy. You just want to find out the parsec value in terms of meter, and given value, it's in a confusing way, the radius of the orbital of earth is given, and you should know that the parsec is the distance between the earth and the earth and the celestial object whenever the angle subtended by the C and B will be is equal to 1 second. That means angle subtended by the radius of the earth should be 1 second. That is the definition for 1 parsec. By using that definition, you can just find the value in terms of meter. Okay. Question number 2.21. Precise measurements of physical quantities are need of science. For example, to ascertain the speed of an aircraft, one must have an accurate method to find its position at closely separated instant of time. This was the actual motivation behind the discovery of radar in World War II. You know that the aircrafts are moving with such a great speed. So, it's measuring its velocity from the land. It was a little bit difficult to track the aircrafts. So, in such a way, the radars have been invented to track the aircrafts during the time of World War II. Think of different examples in modern science where precise measurements of length, time, mass, etc. are needed. Also, wherever you can give a quantitative idea of the precision needed. Okay. So, here actually you know that the range of the mass of the molecule is actually of the 10 to the power minus 30 kilogram. So, the normal weighing balance or weighing machines cannot be used to measure the weight of or mass of a molecule. The actual accuracy for that measuring instrument should be near to the 10 raised to minus 30 kilogram, then only we can measure the mass of the molecule, isn't it? So, such a measuring instrument is there, that is the mass spectrometer that we are using to measure the mass of the molecules, and its accuracy is near about 10 to the power minus 30 kilogram, and that is the required accuracy to measure the mass of the molecule. Okay. We can know that in our normal cases the accuracy is near about 100 grams, 1 gram, likewise it is the weighing machines, okay, or up to milligram also it is possible. The goldsmiths, although the gold purchase, suppose if you are going to purchase the gold and all, there the accuracy is near about 1 milligram accuracy is available in the weighing machine. So, with that one also we cannot measure the mass of a molecule. Actually, the mass of the molecule is 10 to the power minus 30 kilogram, okay, and its accuracy should be near to that value, then only we can measure the mass of the molecule. Now, let us come to the range of the size of the nucleus. The size of the nucleus is 10 to the power minus 14 meter, okay, 10 to the power minus 14 meter. So, its measuring instrument should have the accuracy of about 10 to the power minus 15 meter, then only we can measure that size of the nucleus. Electron microscopes we can use for that purpose, okay. Electron microscopes that we are using to measure the size of the nucleus and all those things. As well, in the case of time, if you have seen the videos of the rocket launching, okay, the descending order, the counting is there, isn't it? At the moment whenever the count 0 came, the rocket started, or the launching of the rocket happened, isn't it? Likewise 3, 2, 1, 0. If you have seen the videos, you may be familiar with that one. So that means whenever the count happens, the time itself the launching should take place. Okay, that means in between there will be a small minute gap will be there, that is of the 1 microsecond. 1 microsecond, that means 10 to the power minus 6 seconds. Okay, that is the accuracy needed there. So that is regarding that question. Question number 2.21. Now let us come to the 2.22. Just as precise measurements are necessary in science, it is equally important to be able to make rough estimates of quantities using rudimentary ideas and common observation. So you know that as a science student, or in the case of the science experiments, accuracy is necessary. But in some cases we cannot take the accurate or precise measurement, we cannot do. A rough arrangements or the rough calculation we will do for some cases, in some cases. Okay. So think of way by which you can estimate the following values. So some measurements, some calculations, needed calculations are given. So using a rough calculation, so rough arrangement, that means with the using a rough values, you have to calculate the measuring, or you have to calculate the given values. Okay. The options are, the first one, a total mass of rain bearing clouds over India during monsoon, mass of an elephant, and wind speed during the storm, the number of strands of hair on your head, the number of air molecules in your classroom. These are the questions, these are the values that you have to find by. So the first one, the total mass of the rain bearing cloud over India during the monsoon. So the average rainfall in India during the monsoon time, it is of 1 meter. You know that the rainfall, the amount of the rainfall is measured in the height of the level of the water. Okay. So that is up to 1 meter, that height is up to 1 meter. The least area of the approximate value of the landscape area of India, it is of 3.3 mega kilometer square. So that is it can be written as 3.3 into 10 raised to 6 kilometer square, and in meter square it will become, that kilometer square you have to convert into meter square. So into 10 raised to 6 will come. So total 3.3 into 10 raised to 12 meter square is the total area. Now you know that the density of the water is 10 raised to 3 meter cube. Okay, 10 raised to density of water, it is 10 raised to 3 kilogram per meter cube. Okay, kilogram per meter cube. So the mass of the water, if you want to find out the mass of the water, that means the mass of the rainfall. The overall rainfall happened in the monsoon season in India. So that is mass of the rainfall happened, which will be is equal to density into volume. Volume is actually the area into the height. Okay, that is the volume. Landscape area, it is 3.3 into 10 raised to 12 meter square, into height, that is 1 meter, and density 10 raised to 3 kilogram per meter cube. And when you are finding out the product of these three values, you can obtain the entire mass of the rainfall happened in India during the monsoon season, approximate value. Okay, all the values that you have taken is approximate only, so the final value also will be almost approximate value. Okay, so that is approximately it will be is equal to the mass of the rain happened during the monsoon season in India, it is 3.3 into 10 raised to 15 kilogram. Okay. Now the second one, there is a mass of an elephant. mass of an elephant. Okay. So, for this one, actually the flotation method is, we are following the flotation method. Actually it was invented, or it was invented by the Archimedes principle. Okay. So, in the first two figures you can see, the first one, it's actually the figure of two boats. Okay, boat. In the first one it is empty. Okay, nothing is there on the boat, just simply boat only, and it's already the bottom area, the area of the bottom surface of boat, it is taken as A, and the depth in which the area dipped in the water, okay, that is D1, that is the depth. Okay. So, the all other portion is over the surface of the water. The portion which is dipped in the water or the water surface, that is of a height or depth, it is D1. Okay. So, we can say here in this case the amount of the water replaced by this area or this portion, it will be is equal to A into D1. That is the volume of that particular portion, and that will be the volume of the water displaced by that portion. Now, again, now we are allowing the elephant to enter in the boat. Okay. So, elephant is also there. You know that due to the mass of the elephant, the boat will sink more. Again, it will sink more. So, then the new height will be, or new depth will be D2. Okay. And bottom area, it is same only, that is A. Okay. Then here in this case the amount of the water replaced will be more compared to that in the first case, isn't it? So, here the amount of the water replaced will be A into D2. Now, we have to find out the difference in amount of the water replaced in the second case and in the first case. That difference will be the, by using that difference we can find out the mass of the elephant. Okay. So, for that, the difference in volume in the second and first case, it is taken as V, then the difference will be V2 minus V1, where V2 is A into D2 and V1 is equal to A into D1. So, A into D2 minus A into D1, A taken as common, A into D2 minus D1, that is the volume, or we can say the difference in the volume of water replaced by the casing in the case second and in the case first. Okay. Now, if you want to find out the mass of the, actually if you want to find, you have to find out the mass of the elephant, that is our purpose, isn't it? So, to find out the mass of the elephant, you have to multiply the difference in that volume, that is V, into the density of water, rho. Okay. So, if you are multiplying the rho into A into D2 minus D1, that will be the excess mass applied on the, or excess force applied on the water surface. Okay. That will be equal to the change in the volume occupied into the density of the water. So, in such a way you can find out the mass of the elephant. So, where rho is the density of the water, A into D2 minus D1 is the change or difference in the volume of water replaced in the second case with the elephant on the boat, and in the first case empty boat. Okay. So, regarding that one, now let us come to the third one, that is C. Okay. C, the wind speed during a storm. Okay. How to find out the speed of the wind during the storm? Okay. So, you are having a pole of height h, on the top you are having a balloon. Okay. So, whenever the storm happen or wind blow, what will happen? The balloon will move, isn't it? So, the distance that balloon moved is taken as x, okay, and the angular displacement in the position of the balloon is taken as theta, that we can measure by using some particular equipments. So, that, to measure, we can measure the angle theta. Okay. So, with the help of this theta angle and h, height of the pole, you can find out the value of x. Also, you have to measure the time taken for the balloon to move from A to B. Okay. So, if these values, if you are having these values, so you know that tan theta will be is equal to AB by OA, that is AB by OA, that is x by h, that is tan theta. So, the value of x will be is equal to h into tan theta, and that is the x value. Now, you have to find out the value of v, the velocity with which that balloon moves. Okay, that will be the same velocity of the storm happened. So, v will be is equal to x by t, which will be is equal to h t tan theta by t, because x is equal to h t tan theta, that we have already derived. So, the velocity, value of the velocity of the storm will be is equal to the displacement divided by the time taken for that movement from A to B. So, h t tan theta by t will be the value of the velocity. Now, the next one is that the number of strands of hair on your head. Actually, I have not included that one here, tricky question only, but easy one only. In that one, you have to consider the area, means as a circular surface, you have to consider the area of the of a human body or human head over there, the hair is there. Okay. That portion you have to consider as a circle approximately of radius 8 centimeters. Okay. The radius 8 centimeters, and you have to find out the area of that circular portion, that will be is equal to pi r square. Okay. Where r will be is equal to 8 centimeter, and the thickness of the hair you have to consider as 10 into 10 raised to minus 5 centimeter, 10 into 10 to the power minus 5 centimeter. You just note down that values. Okay. So, the thickness means the diameter value, you are having the diameter of the hair. So, what will be the radius of the hair divided by the diameter divided by 2, that will be the radius of the hair. Actually, our hair is in a cylindrical shape, isn't it? So, then you can find, if you are having the radius of that hair, one hair strand, then you can find out the area occupied by that hair. Okay. Now, you are having the area of the circular portion over the hair is present, that is a pi r square, that is pi into 8 all square. Okay. 8 centimeter is considered as a circular shape. You are considering the hair or the portion where the hair is there in the head as in a circular shape. Okay. Approximately. And you have to, then total area you are having, and the area occupied by one hair also you are having. So, total area divided by the area occupied by one hair strand will be the total number of hairs. Okay. Just try that one as your own. Okay. Now, come to the next question, that is the number of air molecules in your classroom. Okay. So, volume of one mole molecule at NTP, normal temperature and pressure, that is the natural, means whatever in the atmospheric temperature and pressure, normal temperature and pressure, it is considered as 22.4 liter. So, 22.4 liter is actually is equal to 22.4 into 10 to the power minus 3 meter cube. Okay, 22.4 into 10 to the power minus 3 meter cube. So, you know that number of molecules in 1 mole is equal to 6.023 into 10 to the power 23, that is Na, Avogadro number. Approximate volume of a room, okay, approximate volume of a room of width and length as 10 meters and height of 5 meter. If you are considering like that, then the approximate volume of a room will be equal to 500 meter cube. So, you have to find out the number of molecules in the room. Okay. So, for that, first of all, the number of molecules in the room N is equal to, this is the number of molecules in 1 mole. Okay, volume of 1 mole, the Na will be the number of molecules. Are you getting or not? So in 22.4 liter area, the number of molecules will be is equal to 6.023 into 10 to the power 23. Okay, so for 1 meter cube, okay, if you want to find out in 1 meter cube how many molecules are there, that means 6.023 into 10 to the power 23 divided by 22.4 into 10 to the power minus 3 meter cube. Okay, so if in 22.4 into 10 to the power minus 3 meter cube, if there are 6.023 into 10 to the power 23 molecules are there, then if you are dividing the 6.023 into 10 to the power 23 divided by 22.4 into 10 to the power minus 3, then you will get the number of molecules in 1 meter cube. Okay, so in 1 meter cube, how many molecules are there? This much molecules will be there. So the volume of a room is considered as 500 meter cube. So if you are multiplying that with the value of number of molecules in 1 meter cube into 500, then you will get the number of molecules in a room or in the area of or in the volume of 500 meter cube. That is approximately 1.34 into 10 to the power 28. That is approximate value of the number of molecules in 1 room of volume 500 meter cube. Okay. Question number 2.15. One more time. The famous relation in physics relates moving mass m to the rest mass m0 of a particle in terms of its speed v and the speed of light c. So we are relating the moving mass of a moving body m with its rest mass m0 and the velocity with which that body moving, also the speed of the light c. So these three things, the relation between these 4 values that we are going to derive now. And a boy recalls the relation almost correctly, but forgot where to put the constant c. So he writes the equation as m is equal to m0 divided by 1 minus v square all raised to 1 by 2. This is the equation the boy has written. Okay. So here, if you are doing the dimensional analysis, you know that both are masses. Here on the left hand side and right hand side numerator, both are masses. So as left hand side is having the dimensional formula m, okay, that is for the mass, right hand side should also have the same value. Let us check whether it is the same or not. Here m is there, okay, but denominator, if you are considering the denominator, the 1 is dimensionless, but the v is there now. So for v, the dimension will be m raised to 0, l raised to 1, t raised to minus 1 and all square all raised to 1 by 2. Let us write that one as it is. So square all raised to 1 by 2. The 1 is not having the dimension. So you can see that here the dimensions are not left hand side and right hand side. If you are checking the dimensional formula, that are not equal, so this equation is not valid. So we have to make this one as a valid equation. So that means on left hand side you are having the dimensional formula as m, right hand side should also have the same one, but here on the denominator m raised to 0, l raised to 1, t raised to minus 1 all square all raised to 1 by 2 is there. You have to cancel that one. How can we cancel that one? If you are substituting, okay, the value as, okay, m divided by m raised to 0, l raised to 1, t raised to minus 1 all square divided by the same value. That means they will cancel each other. So, m raised to 0, l raised to 1, t raised to minus 1 all square all raised to 1 by 2. If you are doing like this, then both these values will be cancel each other and the dimension only remaining will be the m. On left hand side m is there, right hand side should also have the m, then the equation will become valid. So, this m raised to 0, l raised to 1, t raised to minus 1 all square is the dimension is of the value c. If you are introducing the c in such a way, m is equal to m0 divided by 1 minus v square divided by c square all raised to 1 by 2, then this equation will become valid. The dimension formula of v square and c square are same, because v and c are velocities. V is the velocity of the body and c is the velocity of light. Both are velocity values. So, they will cancel each other and remaining will be left hand side m will be there and right hand side m0 will be there. Both are having the same dimension of mass, and then the equation will become valid as or on the basis of dimensional analysis. Is it clear now? This is one of the important one, should give some more importance for this question as well, that 2.19. Actually, that was an easy question only. So, in a large paragraph that question is given. When you are seeing that question, you may become wondered, because the question is that much lengthy, but the answer is very small only. We have already seen that one. Okay. As well, the 2.11, so 211, 212, 213, all those equations, that questions are important ones only. As well, 214, checking the dimensional analysis of the trueness of the equations, 214. So, go through that one, and as well the theory portions also, and just finish the notebook with writing the exercise and whatever the PDF files that I have sent you. Should write all those things in the note. Okay. So, we will start the next day onwards. We will start the next chapter. We will start the next chapter on Monday onwards. We will start it. Okay. Motion in a straight line. Actually, that's an interesting chapter. Okay. So, just before we are starting the chapter, you just go through that first 2-3 topics, okay, of that chapter. Then it will be easy to understand the concept. Okay, then, thank you.